let's record this and let's share the screen. So I'm hoping I'm sharing my PowerPoint. Do you guys see it?
Yep. Mm-hmm.
Okay, sounds great then. Okay. So this is from last class. So we defined Newton's law of gravitational force. So that's the force of gravity, let's say, is given by product of two masses and divide by the square of the distance between two masses. Especially when two masses are large, we need to take account that we are measuring from center to center. So when we are here on the earth, for example, if we are standing here on the earth, this radius of the earth becomes that distance, okay? And this product, GMM over R square, becomes the value lowercase g gravitational field strength, okay? But that assuming that we are here on the surface of the earth. If we go above, then what happens? R becomes larger than RE. And our equation in the formula is the R, distance between two objects, right? So this is Earth. This circle is, let's say, Earth, right? It's a sphere. Oh, I have Earth kind of thingy, right? So this is Earth, and this is another object. When it's sitting right on the surface of the Earth, its distance from the Earth is not zero. It is equal to RE, radius of the Earth. But as it goes further, the distance becomes larger than the radius of the Earth, right? So that means value of G becomes smaller. Value of G becomes smaller. So it changes. And for that, we need to come back and look at this equation here. So this is the equation for G. It applies no matter where you are, okay? This G is a special case when you are near the surface of the earth, where mass is the mass of the earth, R is the radius of the earth. But this formula is general, no matter where you are, whether you are on the earth or on the moon or on the any other planet, including Pandora, okay? What happens? This is true. And here, this M is the mass of that planet or anything, okay? That mass. And this R is, let's say, point of interest, a distance of that point of interest from this mass. And if you are at that point of interest, then that's your distance from this mass, okay? So mass here and point of interest is here, it is at this distance r. Okay, so in that case, g is given by this. Okay, so now g depends on these two things, m and r. The uppercase G is constant. It's just a number, tiny number, okay? So we need to just look at this. Now, what happens? If objects are really large, M is really large means G is large. Gravitational field of strength is large. So that means, let's say, if you go to the larger mass object, planet Jupiter, that's the largest planet in our solar system, and drop this, value of G larger, mass larger means value of G is larger, means its falling rate gonna be larger than 9.8 meter per second squared, okay? But it also depends on R. So although mass of the Jupiter is larger than mass of the Earth, at the same time, radius of the Jupiter is also larger. So we have to take account of both of these while actually fully finding those values, okay? And when we take account of both of these, it is still value of G is larger than the value of G here on the Earth. But if we go to the moon, what happens? Moon has way smaller mass. That means value of G becomes really small compared to the value of G here. So on the moon, the value of G is about 1/6 the value of G on the Earth, okay? So Earth 9.8 meter per second square means on the moon it is about 1/6. So when you drop this, it takes a lot longer to reach to the moon surface. For example, if you are standing on the moon, if you try to jump higher on the moon, right? So here, when I try to jump on the surface of the Earth, like jumping 1 foot is kind of difficult for me. Yes, I know you guys can jump way more than that. But on the moon, I can jump 6 times more than that because G is 1/6. Okay, I can jump 6 times more than what I can jump here. So that's what this strength means. Now let's go to the stars. Stars, they have really large mass. Yes, radius is also large, but compared to the radius and mass, when we take account of both, what happens is value of G may be larger than here on the Earth. But more interesting thing happens when these stars die. Yeah, we die. But stars, they also die. And don't feel sad about it. We were born because a star died. If stars hadn't died, what would happen? There won't be any matter to form our body, okay? So we are part of the star. So that's why we are all stars, okay? So I am a star, you are a star. We are stars because we are part of that star. Anyway, when a star dies, what happens? Star kind of bursts, explodes, and the matter goes around. So some goes in the space, but most of them come back because of the gravitational pull. But this time what happens is they come back and forms a really smaller radius. So most of the mass after the exploding of the star, they come back, but the size of the star becomes really small. Why? When a star is not when not dead, it's a breathing. Means it's putting out radius, the fire. So because of that, it's maintaining larger size, larger size. But when it dies, what happens? All mass from this large star can be of this, even smaller than this. So R becomes really small, but mass still remains massive. What does that mean? R decreases means value of G increase. So the gravitational field strength becomes really large. So now I cannot jump even an inch. When I throw a ball like this, what happens? It just goes and comes back really quick. It doesn't go that high because the pull is so strong, okay? In some cases, what happens is, forget about this ball. Even if you shine the light, let's say a flashlight or laser beam, if you shine laser beam here on the earth, what happens? Oh, it goes straight up. But in some cases, when this value of G becomes really large, the beam you shine, rather than going up, what happens? It comes back like balls here on the earth. Okay. So that very large G, where even light cannot escape, that kind of massive structure with large value of G, they are called black holes. Nothing can escape out from there, okay? From the inside of certain region, that's the black hole. So when does black hole forms? When a star dies, massive stars die, then black hole can form. And they do, or they behave the way they behave because the value of G is really, really, really large, okay? So let's just keep that in mind. Keep that in mind, okay? So value of G becomes really, really, really large. So this G is called gravitational field strength. How strong the pull is for a given mass, that's what the G is, okay? Okay. Now let's learn how to use gravitational force to the objects that's moving in the circle. We already learned how to use Newton's law for the objects that's moving in circle. Net force is mass times radial acceleration, right? Net force is mass times radial acceleration. And radial acceleration is just v squared over r, or omega squared times r, depending on what we are looking for, right? How about force? Where is the force coming from? So when things like this go in circle, the force is coming from the tension. And in that case, in the equation, net force comes from the tension. And we saw in some cases, it can be friction. It can be normal force. But when, for example, moon is going around the earth, what is the force that's making it go in a circle? It's the gravitational force between moon and the earth. So now all we need to do is replace this F net by the gravitational force between those two objects. That's it. This side is still same. Okay, so that's what we're going to be doing. That's it. Okay, let's take a look at some example here. So that's the gravitational force between a mass, and this mass could be any mass, mass of the moon, mass of the satellite, or if somebody throws you around the earth, then it could be your mass, right? And this is the mass of the Earth as long as we are talking about objects that's circling the Earth. If we are talking about something else that's circling something else, then that's going to be mass of that object. So for example, here is, let's say, one mass, and there is another mass. And this mass is circling around. This mass is circling around. Means, let's say lowercase mass is the mass of this object that's circling around, and uppercase mass is the mass of the object around which this smaller mass is circling around, okay? So those are two masses when we are talking about circling. So one mass, larger mass, it barely moves. Smaller mass goes around. So when we say moon is moving around the Earth, that means this mass is going to be mass of the moon. And anything that goes around the Earth, we call that satellite. Moon is there naturally, so that's why we call that natural satellite. But we also put artificial satellites, and they go around the Earth. So we can have like artificial satellites or natural satellites, okay, of the Earth. So the FNet is this now for this kind of situation. That's it, okay? And depending on how far we are, and if we want to measure that height from the surface of the Earth, then we can replace R by RE plus H, right? So if it is there, height is 0. That means R is just radius of the Earth. When it is up there, then in that case, what happens? Now, the distance is radius of the Earth up to this point plus height, H, from the surface. So basically it's this R, but we are just breaking R into two parts. That's it, okay? The distance between Earth and the object measured from the surface of the Earth, let's say, and then that distance is going to be height, and this is already there. We are already that distance, that far from the Earth. Anyway, so that's what you see here in this sketch as well. So now let's use that equation. See, this side we've been using, and now the force is just that. And force is towards the center, acceleration is towards the center, so both of them have same sign, okay? So we can assume positive and write equation like this. Now what happens? From here we can calculate speed of the object that going around the Earth, okay? And turns out the mass cancels. The mass of the orbiting object cancels. So how fast it goes does not depend on its mass. That's kind of interesting, okay? So a smaller object, larger object, as far as they are at the same distance, what happens? They go with the same speed. Looks like one of the R also cancels, but not whole thing. One of the R cancels. So we can rearrange this and get the speed. So what is this? This is the speed of the satellite. This satellite can be artificial or natural. If we know the distance, how far we want that satellite to go around the Earth, that means we know how fast it has to be moving to go in circle. Otherwise, it's not gonna stay on that height. So we can do the calculation and put that in the rocket and put that in the orbit. Once it's in the orbit, give that speed, give a boost one time, and it's just gonna keep going round and round the Earth with the same speed. Okay, so that's what it means. And this v is the speed around this orbit. If we know, since we know the radius of the orbit, we can write that as a distance 2 pi r circumference over time as well. So by doing that, we can find the time, okay? So that's where another one, the Kepler's law comes in, okay? So it's not just between Earth and its satellite. Earth is, we can think of Earth as a satellite of the sun because Earth is going around the sun. So if we're doing that, then we can replace this mass of the Earth by mass of the sun. And r going to be distance of the Earth from the sun. And that's going to give you the speed of the Earth around the sun. So all we need to know is mass of the sun and distance of the sun from the Earth. You can tell how fast Earth is going around the Earth. You can calculate that. So that's how this formula is used. It's not just for the Earth satellite. It can be the speed of satellite of anything, okay? So anything, that's going to be the mass of that thingy, and r going to be the distance of the satellite from that thingy. That's it, okay? So now let's look at our natural satellite moon. We have only one moon. So it says orbital velocity of moon is that much. Oh, it's given in kilometer per second. Maybe we want to convert that into meter per second. Oops. 1.023 times 1,000 meter per second, right? So what happens? You look at the moon and you can see the moon is moving. You can tell, you can look at the, you can calculate. If you are careful observer, you can calculate the speed of the moon, okay? Just calculate how far it moves. So anyway, so if you can calculate that speed, then you can tell how far the moon is from the Earth. And it's talking about center of the Earth. That means we are just looking for R, okay? If it said surface from the Earth, then we would be looking for H. What's the difference? This is from the center, from center. This from the surface, from surface. And how R and H are related? R is RE plus H. So it depends. So it depends on problem whether you're going to be using H, this, or just R. So in this case, it just says from the center. So that means we are just looking for R. Okay. R is what? So we learned that V is G times mass of the Earth over distance. GM over R. Did I get that formula right? I had that in last slide, okay?
Yeah, we've got it. And that's what I've got written down. The 1.023 times 10 to the third times G over R.
Right.
I did the square root, yeah.
That's right. So since we are looking for R and it is under the square root, it's a good idea to square both sides and get rid of that square root, right? Now we can solve for R. So we know everything. Mass of Earth is given there, and G you can find anywhere. I think that's 6.67 times 10 to the power negative 11. You plug that G in there, mass in there, and that speed in there, and you should get R. And you're gonna get that in meters, okay? And you can convert that into kilometer by dividing by 1,000. And that's going to be kilometer. And that's what you should get, I think. Okay. Okay, so that's how we can find how far something is. Or if we know how far something is, we can tell how fast something is moving. Okay. If we were to calculate the speed of the Earth around the sun, what do you think we'll get? Any idea, tentative? Can you make a guess? You can type that on the chat if you like. Here we got what? The speed of the moon around the Earth is around 1 kilometer per second. What do you think the speed of the Earth is around the sun? Any idea?
Not much. Oh wait, the speed of the Earth around the sun? Oh,
Yeah,
quite a bit.
quite a bit. Give me some number estimate. Throw some number. Four times, 10 times.
Well, hold up. The moon orbits the Earth once every day. The Earth orbits the sun once every year. I don't know. I think it's a lot slow. Wait. It might actually be a lot slower. It might be like 1/365th.
Actually, moon is not orbiting Earth every day. It takes a month for a moon to go around the Earth.
Okay.
Yeah, it's just a guess, right? And I think it is around 30 kilometers per second for the Earth to go around the sun. Think about it, how fast you are moving around the Earth. Earth going that fast and we are on the Earth, aren't we? That means we are moving that fast around the sun. Do you know how much is 30 kilometers per second?
Let's see. That's from here to another town over every second.
Yeah. So it is around 20 miles if 30 kilometers doesn't make sense, right? So nearly 20 miles every second. Think about that. When you are driving 60 miles per hour, you are driving every mile per minute. And here you are going nearly 20 miles per second. Multiply that by 60, that's how many miles you are going per minute. That's how many times faster you are moving around the sun compared to your speed when you are in freeway.
For comparison, that's 108,000 kilometers per hour.
Ooh, see? Yes. So, yes, we are going really, really, really fast, but our ride is really smooth. See, no friction, no road friction, right? So no noise. And Earth never puts brake on or hits the gas pedal, okay? So because of that, very smooth ride. So even when it's moving so fast, we don't feel like it, okay?
Isn't the big problem everybody wants is to keep other objects from exacting a net force on Earth, like an asteroid?
Yeah.
Isn't that what everybody's afraid of?
Right, that would be like suddenly putting, let's say, brake on fast-moving car. Really fast-moving car.
That would be a very bad idea.
Right. Okay. Okay, so now we can find the time by replacing B by period, just like I talked about. Okay, so B by something like this. So we can, from this equation, go there. And if you want to calculate how long it takes, you can do that. Okay. So what's the period of the Earth around the sun? 1 year, 365 days, right? And if we plug in that, we can find how far sun is. So that's how we can use it, okay? So this gives the relationship between distance and time. But this is r cubed and this is t squared. Bit complicated relationship here. So that's how we knew, okay, farther the objects are, it's taking longer to go around, period is getting larger, okay? So objects are moving slower. Another way to look at it is go back to this equation. Farther the objects are, they are moving slower. So that's why the planet that is closest to the Earth, sorry, sun. Which one is that? Is that Mercury? Yeah, it's moving fastest. It takes only 88 days for Mercury to go around the Earth. But for us, it takes 365 days. For Jupiter, it takes 10 times more than the Earth because it's farther, okay? So anyway, so similarly, we can find the time as well using this formula. Looks a little bit complicated here. So that's called Kepler's third law. And Kepler got this equation by mapping the position of these different planets on the sky, okay? At that time, Newton's law of motion and Newton's law of gravity wasn't discovered. Right now, we know Newton's law of gravity, Newton's law of motion. By combining both, right, we got these equations. And it turns out to be correct, okay? So Newton was able to derive, mathematically, systematically derive the equation Kepler got just by doing experiment, okay? Just by doing experiment. And turns out to be really nice, they agree, okay? So now we can put satellites around the Earth so that we can receive the signal from there. Probably you may have heard satellite phones, satellite TV. So what does that mean is, rather than coming the signal from the local stations, what happens? It comes from this global stations, and those stations located around. So what they do is they transmit the signal from Earth to the satellite, and satellite retransmit back to the Earth so that it covers larger area. So to cover 360 degrees, you need at least 3 such satellites going around, okay? So any communication company that has worldwide coverage, let's say, they have at least 3 satellites going around the Earth. And we don't want those satellites wandering around everywhere on the top of the Earth. So for example, let's say you put a satellite on top of Denver, and if it does not remain on top of the Denver all the time and goes, let's say, in the sky of, I don't know where, let's say Russia, then they're gonna shoot and, you know, bring it down. So you want your satellite to stay right on top of your sky, right there, okay? So how do you do that? You match the rotation rate of the satellite with the spin rate of the Earth. And 24 hours is the spin rate, okay? So if sun is here and Earth, sun is there and Earth is there, 365 days is the time it takes to go around and come back, right? Now, one day or 24 hours is just the spin. Earth is not just going around the sun, but it is also spinning about its own axis while going around. So it spins once every day. So that's what sunrise to sunrise, for example. Okay, so that's how we see sun rising. Okay. So sun is not going around the earth, but it's other way around, right? So anyway, so that's the idea. So that time, once we put that time, what happens? The satellite appears to be always on top of that, and that's called geostationary satellites, okay? So that's how we get signal from those satellites on the dish antenna and can get that in the TV. But there could be these big antenna sitting outside the town, and this may be just receiving from there. Okay, so that's what usually happens to the local this dish antenna you see in in our homes. Okay, it's not receiving from the satellite there. It's just what happens is there is a big antenna somewhere outside the town. It gathers signals and send that signal to our home, this one there. Okay, so
Oh
that's
yeah,
how it
cable.
works.
Mm-hmm.
Or through the cable, yes.
No, that is cable. You just described modern cable communications for
Right,
TV now. Yeah, that's
right,
what they do.
right. But here, this small one, there can be tower somewhere in the side of the town, and it may be just receiving from there. That can be also this kind of setup.
Oh, I've never heard of that setup. Huh.
So if it's, yes, it can be coming from the satellite directly like that as well from there, but some may just be a bit creative and put somewhere there and distribute. Okay, so anyway, how far it has to be then? See, if it has to be staying right on top of that, then how far it has to be, right? If you put a little bit lower or higher than that, it's going to drift apart. It's not going to stay right on top of that particular town or place, okay? So if you want to calculate that, you can plug that time here and solve for the distance. So that's how this one comes in handy, okay? Here, there is this example. So all these artificial satellites at same height, okay? So they are at same height. They have to be at same height. It cannot be one here, another one higher than that. It cannot. So what happens is it's like a satellite highway. But this highway can go circling around several different ways. But you have to make sure that one doesn't hit another one when it crosses. So if there is just only one orbit, then what happens is like all of them, one is there, another one is there, another one is there, and going with the same speed. So what happens? They are fine. If something hits one of those and it slows down or it speeds up, and that may cause problem, accident over there. Okay, so now here is a question for you based on what we just discussed, okay? Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. Less than, equal to, greater than, and need more information as well. Okay. One has larger mass. Larger weight means larger mass, right? So why many of you think speed is same?
Both of the satellites are in free fall at the same height. They've been free falling forever, and there is no air resistance. So, if the gravity is the same, and there's no wind resistance, and they're always free falling, eventually, despite the mass, it's going to be the same speed.
Okay, so that's one way to explain it. Can we explain that based on the equation we wrote?
I think you're getting an answer in the chat, Dr. Dungana.
I am.
Yeah.
Mass of satellite is negligible in speed equation. Okay, is it negligible or it is not there? Remember mass cancel, right? Yeah, mass cancel. Mass of the satellite cancel. Only mass of the host thingy matters, okay? So mass of the satellite doesn't matter, so that's why it's equal. It simply depends on height. So if it is not geostationary satellite, you can put that in different heights. But if it is geostationary, then it has to be at a fixed height. So anyway, so that's about the circular motion and gravitational pull and use of circular motion or Newton's law for the, using the gravitational force as a net force. And this is not for just for the Earth, Moon, or our planetary system. This thing is true for any massive object, smaller mass or larger mass, whether it's on the Earth or on different galaxy. Okay, so that's why Newton's law is also called universal law of gravitation. It is valid no matter where you are. For any two masses, it's valid. Okay, so now let's move to another chapter. We have some work to do, and I saw that a dad's joke, huh? So that's how bad my jokes are then? Okay.
I think that's what he's implying.
No, they're funny like dad jokes. I love your jokes, Dr. Dungana. They're all puns. They're punny.
I don't know what jokes. Dad jokes means really when we label jokes as a dad joke.
they're like punny jokes, like jokes that are puns.
Okay. Okay. So let's do some work then. But how do you calculate how much work you did? We want to quantify things we do, right? So you already saw this equation. Work done is given by force times displacement times the cosine theta. So I simply would like to emphasize the fact that this theta has to be always the angle between this force and displacement. Okay. So not any angle, but look for the angle between force and displacement. So because of that, whenever you are asked to calculate the work done, you want to draw a force, which way the force is acting, which way the displacement is there, okay? And find the angle between them and use that angle as theta. So theta is not any angle, but the angle between force and displacement, okay? So work depends on these three things. One, value of force, value of displacement, and the angle. So cosine can be 0, cosine can be 1, cosine can be negative numbers between 0 and 1. That means work done can be positive or negative. Work done can be positive or negative depending on angle. And remember, while using this formula, we don't put sign for the force, we don't put sign for the displacement. We just put the values. Force and displacement, they are vectors. So sign means direction, but here we are calculating value. So we are just using values here. Now, work done has a sign though. You may get positive or negative, and that sign gonna come from this theta, and theta depends on the direction of F and D. So we are taking account of the direction of F and D indirectly in terms of angle theta here, okay? So that's how we use this formula. Formula itself is simple, but using it could be tricky. As long as we are following the or doing it correctly. Draw force, draw displacement, figure out angle, and use that angle, okay? Do not just assume any angle is the angle that goes in this formula, okay? So as long as you keep that in mind, you should be fine. So yes, that is D displacement and can be written as delta x, but we are just putting the value there, okay? Now, this cosine theta can be, paired with the force, and we can write F cosine theta, for example. So when we do that, it looks like a component of force, right? So for this force here, F cosine theta gonna be this, the component that is pointing towards the displacement. So that's what this parallel means here. So this line, double line here, these are parallel line. So we are indicating that by writing parallel force, okay? So that means the force is parallel to displacement. That means they are in same direction. When that's the case, work done is simply F times D, force times displacement. When they are pointing in the same direction, we don't need to worry about cosine because theta is 0, cosine 0 is 1, okay? So that's that. Another thing you want to keep in mind is work is a scalar quantity. It doesn't have direction. So when we get negative value of work done, what does it mean? For the vectors, negative would mean a direction. But since work done is a scalar, it does not mean it is a direction. So what does negative positive sign means in a work done, and how do we treat it? Any idea?
Could we say that negative work means less work is being done, so an object could be slowing down?
Yeah, less work. Yes, just like a number. Yes, good idea. Okay, less work means, yes, so negative number, larger negative number is smaller than bigger negative number, and even smaller than 0 and positive numbers, right? So they work just like regular numbers. So negative 10, positive 10, negative 10 smaller than positive 10. So that's how we need to treat it, okay? And when we are adding work done, we keep track of those positive sign, negative sign, and add them. So we don't need to draw a arrow to add them. That's the nice thing, right? Okay, so just like I was saying, it depends on 3 different things. So work can be 0, positive, or negative. So when is the work done 0? 1, if no force is acting, then work done gonna be 0. And by the way, when we say work done, always ask work done by what force. It's the force that does the work. You may be saying, okay, I'm doing work, but while using this formula, think in terms of, okay, I'm applying force, and the force I'm applying is doing the work. I'm not doing work. Think in terms of that, okay? So that's going to be easier to hopefully use it, okay? So, but yes, of course, you are applying force. So while talking a bit loosely, we can say, okay, I'm doing the work. And we're going to be using that kind of wording as well. But while using the formula, always think that work is done by a force. If force is not there, of course, nothing is doing work. That force is not doing work. And no matter how much force you apply, if there is no displacement, no work. So for example, I'm pushing my chair starting from 12 o'clock today, okay? So I'm applying that mg force, but chair is not moving. There is no displacement. Means I'm not doing that work there, okay? So you may be pushing a wall with really large force. If the wall doesn't move, you didn't do the work. Work done by you is 0. So that's how it works, okay? Now let's take a look at this painting here. In this painting, we see this person is carrying a large load and walking. So there is displacement, there is force, but even with both force and displacement being there, work done can be 0. And that is because of the theta. Cosine 90 degree is 0. Means if the angle between force and displacement is 90 degree, work done is 0. Okay, so in this case, what's happening? The displacement is horizontal and the force on lifting that weight. So if I am, my weight is there, so that means I am pushing it up there. Okay, so force is there. Force is up, and if it is moving that way, that means the work done by that force is 0. Why? Because angle between that is 90 degree, cosine 90 is 0. So that person is not doing work in this example. So meaning of work done in our daily life versus meaning of work done in physics could be different. And that may cause problems sometimes. So for example, if I'm working as, let's say, security guard somewhere in front of, I don't know, let's say a bank or something like that. If I'm standing there all day, in our daily language, yes, that guard is doing work, getting paid. But physics says since the displacement is 0, work done is 0, no work. Okay, so that's the difference there, okay? Okay. Now work done starts getting negative when the angle between force and displacement becomes larger than 90 degree. Larger than, oh, do you see that? Larger than 90 degree. And maximum negative when angle is 180 degree. Cosine 180 is -1. So maximum negative. Okay. So for example, here, what do we see? This bucket is being pulled up by the tension. Okay. So work done by tension is not 0, not negative, it is positive because the angle between tension and displacement is 0 degree. So work done is force, which is tension, times that displacement, and it is positive. But if we look at here, there is gravitational force acting, and gravitational force always acts downward, right? And displacement is up. So gravitational force is down, displacement is up. So the angle between them is 180 degree now, means it's doing negative work, maximum negative work. So gravitational force is doing negative work, tension is doing positive work. So that's why we have to be, we have to watch carefully when we are asked to find work done. Work done by what force? Always ask that question before you actually start doing or solving the problem, okay? So now here is this question. And you have, and there are certain cosine values that's going to come out handy just in case. So cosine 0 is 0. Oh, not 0. Sine 0 is 0. Cosine 0 is 1, positive 1. Cosine 90 is 0. And cosine 180 is negative 1. Okay, so these three cosine values, we may be using, we're gonna be using this a lot in this chapter. Okay, so keep it somewhere, either in your head or in a paper next to you somewhere. Okay, it's gonna come out handy. So now here is this question, and you have a minute to answer this question. Oh, forget to warn. 20 more seconds, folks. In 5 more seconds. 5, 4, 3, 2, 1, and it stops. So did you ask work done by what force? And which direction the force is acting? Did you draw it? If you did not, go ahead, draw it now. Okay? Please do so, okay? So which way the force applied by Newton is acting, draw it, okay? And displacement, which way is the displacement? Draw it, okay? So now, since you already drew it, how about you type me either up or down for the direction of force? Is the force up or down in this case while lowering the book? Up or down? Type it, folks. Go ahead. So force is acting down based on what we see. So force acting on the book is down, right? Force acting on the book, the force applied by Newton is down, right? Okay, so that sounds great. Now, do you have something, a book near you, or book, or let's say some sort of thingy? I have a remote control. Hold it like this. and then lower it. Or could be a water bottle. Yes, I see Robert is holding water bottle. Lower it. Are you applying force down? Are you applying force down? Are you applying force down? Try applying force down. What happens? Does the thing lower slowly or goes really fast? So now think about, is Isaac Newton really applying force down?
He's applying force opposite the direction of gravity.
Yes, so that's why if both forces were down, force of gravity down, let's say you apply force down, oops, net force would be down, the acceleration going to be larger than g there, isn't it? mg
Yeah.
gives you g acceleration. Now you add force downward, what's going to happen? The acceleration would be larger than g, isn't it? But it's not accelerating, it's slowly going down, isn't it? So that means you have to counter the gravitational force, isn't it? So that's what you are doing, right? So
We are doing work opposite of the direction of the other work.
gravity, right? Right. So that's what we are pushing it up, actually. We are holding it up. So that's why it's coming down slowly, okay? So that means force is down. Oops. Force is down and displacement is down, means angle between them is, oh, force is down? No, up. Force is up and displacement is down, means angle between them is up force, displacement down. It may look like free body diagram, but it is not free body diagram. Remember, displacement is not a force. So this is just a sketch to determine the angle. So theta is 180 degree. 180 cosine means negative. So that's why the work done is negative. Okay, so we haven't checked your response. Let's see, how did you guys do? It's everywhere. So yes, it may be simple, but it can be confusing. So we need a lot of practice. So that's why I'm giving this emphasis here, okay? So let's take a break. And when we come back, we'll go through this kind of thing more, okay? Exercise, we'll do more this kind of exercise. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. I just noticed on the chat there is this question. I thought there was no work with constant velocity. It was for the previous part of this slide. That's a very good question. Anybody has any response on that? Okay, so Kral answered that, but anybody has any thought on that? I thought that that is very, very good point. Or we can come back to that a little later, okay? But for now, let's take a look at this one here. So let's see what we did here. So again, the varieties of answer. And of course, this question is not so easy as well. So what's happening? Where is the work? Where is the force of gravity? Force of gravity is acting downward there. And with respect to force of gravity, if we look at this, the displacement is in that direction. So force and displacement. What's the angle? Do we know angle here? Angle between D and mg. We know this theta is the angle made by this incline, that's theta, and there is this 90 degree. So the angle between mg and displacement is 90 plus theta. So that means when we use that in formula, it's going to be cosine 90 plus theta. What is it?
That's negative.
Negative what?
Between -0 and -1.
Oh, -0 and -1. Yes, so it's larger than 90, means the work done has to be negative. So there are two answers with the -1. So how do we determine which one is the correct answer here? So if you remember a trig identity, which I don't expect you to remember, but just in case, if you happens to remember, then we know this cosine 90 plus theta is sine, negative sine theta. So if we were to use that, then it's going to be FD negative and sine theta here, and d sine theta becomes same as H, right? That being the opposite. So this being D, and sine D means opposite, H. And so we can replace d sine theta by H and write F times H negative, and F here being M times G. So that we get D as the answer. So that's one way to look at it, but to use that, you have to have that thing in your head. And just like I said, I don't expect you to remember that. So there are way around of not using that, okay? So let's take a look. Another way to look at it is think in terms of, let's say, the component of mg. Okay, let's see here. Remember how we, draw a free body diagram? Kind of similar, but mg is not lining up with the displacement, and it is making larger than 90 degree. So to make it bit, a bit easier, what we can do is we can find the component of mg and look at the work done by components, okay? So for example, here, this component gonna be mg cosine theta. And another one, which would be this, but we draw here, means that's gonna be mg sine theta, okay? So now, once we have components, we can forget about the mg. So what we can do is we can find the work done by both components and add them together. So rather than just pushing by one hand, let's say thinking in terms of pushing by one hand, you can think in terms of pushing by two hands, but they are perpendicular to each other, 90 degree. Oh, my camera doesn't catch 90 degree. So they are 90 degree with each other. Okay, something like that. So rather than just saying, okay, I'm pushing this way, I can say I'm pushing this way with one hand, pushing this way with another hand. So that's like a work done by two components of the force. So now let's take a look at one component at a time. So for that, I can draw the displacement is still pointing in that direction. So now I know the angle between mg cosine theta and d. The cosine component and d, the angle between them is 90 degree. So when force and displacement are 90 degree, work done is when angle is 90 degree, work done by that force is 0. Yes. So that means this thing is just sitting there, not doing the work. So only thing that's doing work is this force here, mg sine theta component. So now if we look at just these two forces, what's the angle between them? 180 degree. So now we can write, okay, the force is mg sine theta and displacement is d. So this is force, component of that force, and that's the work we are finding, work done by that component of force we are doing, and displacement and cosine of angle between them. What is the angle? 180 degrees. See, the theta goes somewhere else, not in cosine in this case. Cosine 180 is -1. Okay, work done is this. So that means cosine 180 -1 means negative mg, and I can write d first and then write sine theta. Since they are multiplying each other, I can move, right? So d sine theta, as this one said, is h. So it becomes negative mgh. So that's another way to look at it without remembering this identity. I'm pretty sure there is another way of explanation and somebody is trying to explain that. Am I thinking right? Somebody is trying to explain slightly different way. Cannot it be easier? Shouldn't there be easier way to do than this? Anybody thinking about that and trying to explain that?
I just have a question about the direction gravity affects the displacement. If it's being pushed up, will it always just affect like the y value and not the x?
Mm-hmm. Yeah, this y component is there. It's just balancing the normal force. It's not doing work. Rather, it's just balancing the normal force. And normal force doesn't do the work either, of course. Okay.
Okay, thank you.
Okay. So yet another way to look at it is that mg is pointing down. So for the mg force, we can think of, okay, this thing, when it went from here to here, we can also think, okay, it went from this height to that height, means it went through this height there. So we can think of, okay, displacement is that, and mg is that. So that means angle between them is 180 degree. So force, so work done is mg times d times cosine 180 degree, which being -1, you get negative mgd. That's yet another way to do it. So yes, of course, there are more than one way of doing it, okay? But by showing all these, I'm hoping you are catching up, how do we find the work done in different situations. And worksheet has very similar problem like this, okay? So it asks you to find work done by different forces, individual forces, okay? And so I think it's good. It's a good idea for you to, go there and do, calculate the work done that the worksheet is asking you to do, okay? And the idea is exactly same. See if you remember and can do that. And it also asks you to find work done by all forces, add them together. And that's where that constant velocity thingy comes in. So constant velocity means net force is 0. So that means work done by net force is 0. So when we add work done by these different forces, in this case, we should get 0 as the answer, total work done. But again, we have to ask work done by what force? So this one asked for the work done by this F force. The second question here asked for the work done by a gravitational force, right? So similarly, if you were asked to find work done by net force, then there are two ways you can do it. First, find the net force and find the work done. Second, find the work done by all forces and add them together. Either way, you should get the same answer. So that's how we do it, okay? So now here is yet another question about work done. And no mathematical calculation is necessary here. So maybe 30 seconds is going to be a good time for this. So total 30 seconds, folks. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Again, we have varieties of answer. This calculating work done proving harder than any other question looks like, okay? Yeah, that's why I have brought a lot of questions. So let's suppose I'm thinking A as the correct answer. Why am I right or wrong? Can somebody help here?
I've got an idea. Oh, go ahead. Go ahead.
Okay, I was just gonna say that I think you would be wrong because work is equal to FD cosine theta. So if we just look at the cosine theta, the angle between the string and the rock is gonna be 90. Like, and the direction it's moving, yeah, and so then that's gonna make it equal to 0.
Oh, force and displacement, angle is 90 degrees. Oh, never thought about that. So that's why I chose A, huh? So yes, you are right. So angle between force and displacement in this case is 90 degrees. When something is moving in circle, remember the displacement at that point, at that moment is tangential to the circle, okay? So yes, looks like it's going to be 0 and C is the correct answer. I was wrong. And thank you for very good explanation there. Okay. Now, let's go to the gym. Let's go to the gym and do some workout here. Okay, weightlifting. And you have 2 minutes and 30 seconds, 2.5 minutes to answer this question.
Can I clarify something, Dr. Dingana?
Yeah.
So in the third part where it says puts it down, do you mean just lowers it down or puts it down on the floor?
Yeah, lowers it down.
Okay, thank you.
Up, holds it, and brings it down. 3 actions, right? Oh, 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. I received a private message on the chat. Looks like I forgot to mark correct answer for a particular question. Well, let's see if I know how to go there. Oh. No. For polling, how do I go back? Quizzing. Now I'm going to lose the previous response there. Oh. No way of going back. Oh, I can go back, I guess. So I think we can check after we check this one here. Okay, so let's check what happened here. So we are getting better, but I don't know if it is in the right direction or wrong direction. But I like to check the another question. Here looks like I didn't check the right answer. And I think it was D that was right in this question. It's gravity question, I think. Okay, so in this case, So lifts up, force up, and displacement up. Work done is positive, F times D, right? Work done. So force up. So while going up, so force is up. Force is up, displacement is up. Means work done is, work one is F times D. Okay. So now holding it means displacement is 0, means work done while just holding it is 0 because displacement is 0. Now down, force is still up, but displacement is down now. See, you cannot push it down while lowering it down, right? So it's like a Isaac Newton problem, lowering the book, right? So even if you are lowering something, you are still applying force up. You are still holding it up. So the force, displacement, and cosine 180 degree. Why? Because force is up and displacement is down. Okay, so the angle between them is 100 degree, means this is negative F times D. So negative is smaller than 0 and positive. So that means W1 is largest and W3 is smallest, and W2 being in between. So it looks like it is straightforward, this one there. Did I get that right? Looks like that is, yes. So that's how we need to look. And if you did not get that right, no worry, there is another one here, okay? Similar and even easier, maybe. So this is pull force. So pull across. So that means displacement is in that direction. So let me give you that, okay? So now I'm giving you 1 minute and 30 seconds for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So mostly C. Getting better. Let's see if the C is the correct answer. Work done by normal force and force of gravity is 0 because displacement is making 90 degree with both of those. So that means they must be equal. And work done by pull force is positive because theta is 0 for this and theta is 180 for friction force, means the work done is negative. So that means this must be largest and these two equal in between, and that's that. Okay, so yes, C is the correct answer in this case. So what happened? Did I choose the wrong answer in one of those? Isoscelas.
You got it right.
Okay, so it looks like it's fine. Okay. Okay, folks. So I hope I covered many scenarios of work done by different forces. Keep this in mind and do the worksheet. Okay. So before we wrap it up, what does doing work done means? It changes the energy of the thing. Okay. So for example, if I keep pushing thingy, what happens? It speeds up. Let's say with the net force, if I keep pushing it, what happens? Its speed changes. So how do we write the relationship between change in speed and the push? So one way, use Newton's law and find the acceleration, find the speed, right? That's one way. But there is easier way, and in some cases it becomes a lot more easier than using the Newton's laws. Okay, so that's when we use the energy concept. So by doing work, what we are doing is we are changing the work of the thing that we are doing work on. So if I'm pushing something and it's speeding up, that means I'm making its energy larger by giving my energy. Okay, I had my lunch and I'm using that energy, transferring that energy to that object when I'm doing work. Okay, so that's another thing. So when we are doing work to the system, what happens? System's energy increase. But if the system is doing work, then in that case, what happens is it's giving up energy, means its energy is decreasing. So that's what negative and positive work means. Okay, so for example here, weightlifting, yes, that's another example. This guy is spending lunch or breakfast, I guess I should say everything. That's how much work this guy is trying to do, right? So what happens here? You run, means again you are spending your energy here to speed up, and then you can change height over there, go higher, okay, by using that energy. So this gives you one kind of energy, and when you are changing height, that's another kind of energy. And there is this, you are again doing work. The energy you are doing, work you are doing is stored as energy on the string of that bow, right? So here, when you are jumping up in this high jump example, your energy now, what happens? The energy you supply brings you higher height, and when you come down, bam, on this one, this floor, that different kind of energy, that energy is being converted into different kind of energies. So there are these different kind of energies, and total energy we call the energy of the system, and one could be kinetic energy, another could be potential energy, yet another could be thermal energy. For example, when you rub your hand, you are doing work, and that work is coming out as a heat. That's thermal energy. And chemical reaction, if you have taken chemistry class, done some lab, I don't know, take home lab, you may have seen, you know, when there is a reaction, sometimes you have to heat those reactants. Sometimes you don't have to, they just give up more heat, okay? So that's a chemical energy. So there can be several kinds of energies, but for this class, for this part, for now, we're going to be focusing on kinetic and potential energy, okay? So if gravitational force is doing work, the energy stored is called gravitational potential energy, right? And if by doing work, speed is changing, we call that kinetic energy. So there are two kinds of energy. We're going to be mostly focusing on this. So yes, we'll talk a little bit about thermal energy. So that's all. So we're going to pick it up from here next class, okay?
Thank you.
Thank you, folks.
Thank you.
Thank you.
Thank you.